So let's start. Let's get into discussion. Why ontology? Why is that important? What is ontology? And then we spend a little time on agency and consciousness, on the experimental agent, and then finally finishing up with the specifics of the Bohm centennial and where this might lead and where this might go in the future. So why ontology? What is ontology? Simply put, ontology is a theory or study of what exists, what is real. Being, existence, nature, reality. And this seems to be a really important topic to science, because we're saying science studies the nature of reality. But as we'll see in quantum physics, quantum mechanics, that's a disputed concept, because maybe quantum mechanics is all about just describing measurement outcomes, an operational procedure, an epistemological procedure that tells us nothing about reality. And that was the position that Niels Bohr often took, and von Neumann often took, and Jordan and Born. And so we're going to look at the contrasting views of ontological approaches to epistemological approaches. Of course, coming from the Greek ontos, being that which is, it's a branch of metaphysics. And so why even metaphysics in quantum physics? And of course, Abner Shimoni always talked about the word experimental metaphysics, that quantum measurement experiments actually are testing metaphysical assumptions, not just physical assumptions. What does that mean? Normally, when people hear the word metaphysical, they think, oh, we're talking about mysticism. It's irrational, it's a transcendent, it's esoteric, it's spiritual. But really, metaphysical is a philosophical discipline and refers to the analysis of the first principles, the foundational assumptions, which inevitably underpin any scientific analysis of science. So you always have a metaphysical assumption, whether you're aware of it or not, when you do science. So, importantly also, metaphysical assumptions essentially constrain the application of any mathematical theory to quantum phenomena. They very often simply represent the worldview of the scientist that they bring to the table when they engage in these concepts and the analysis of these concepts. So what are metaphysical assumptions? One very familiar one, you could ask, what rules physical reality at its most fundamental level? That would be a metaphysical question. And one core assumption by many quantum physicists is indeterminism. The idea that a physical event in quantum physics represents intrinsic randomness, objective chance, absolute unpredictability. And that's a metaphysical assumption you're making. Oh, the universe is indeterminist. And that is sort of the textbook view, for the most part, that's being taught in most quantum mechanics courses. And quantum mechanics prides itself that it discovered the absolute, the rule of objective chance in the universe. But of course, that's not proven. That's an assumption. The other one is, the opposite to that, is determinism. And of course, David Bohm's theory is a deterministic theory, a hidden variables deterministic theory. So how might that work? Hasn't quantum mechanics disproven this old concept of determinism? And we're going to make the case, no, it hasn't. So determinism simply means any physical event is entirely fixed and predetermined by the history of the past events in the universe. And then, this leads to cosmic predetermination, clockwork universe. There is no freedom. So that's why people resent the idea of determinism, because they feel like it locks everything down, there's no creativity possible, and so on. But this is a misreading of determinism, and this is where emergentism comes in. In emergentism, in the theory of emergence and self-organization, I'm going to talk a little bit about what that means. A physical event results, yes, from a deterministic process, but one whose outcome is not predetermined and is effectively unpredictable, like in deterministic chaos, for an example. So we've coined the word, Gerrit and I, in our discussions, that is really helpful to us. We're really talking about determinism without predetermination as a possibility. And that comes from emergence theory. And this is a book where and already in this book, co-authored by David Bohm with Basil Hiley, who's going to speak right after me and go deeper into this, David Bohm and Hiley point out the close resemblance between key properties of deterministic hidden variable theory and chaos, complexity, and emergence theory. And emergence theory describes, of course, the emergent formation of ordered or negentropic states in nonlinear self-organizing systems, such deterministic chaos. Let me tell you I just want to mention 3 slides or 4 slides, because I won't come back to this topic, except on Saturday in my talk briefly. But let me just frame this. Emergence comes under many, many names: complexity theory, chaos theory, self-organization theory, nonlinear dynamics, fractal set theory, cellular automata, synergetics. And the key characteristics are sensitive dependence on initial conditions, global order from local randomness, and indefinite to definite state transitions. So you have a higher global order level that is visible, the macroscopic observable structures, and then you have local microscopic interactions, which spontaneously organize into wholes and ordered wholes. And of course, the last 30 years, we've seen an explosion of interest in this field. But the application of these ideas to quantum physics, to the problems we have in quantum mechanics and explaining quantum phenomena, has been very limited. And so we try to pioneer that approach even further. Also related to this is non-equilibrium thermodynamics. And importantly, these refer to self-referential recursive processes, which are computationally non-reducible in many cases. So what happens is, where does the unpredictability come from that I've been talking about? It comes because of the intrinsic self-reference of these systems. And an analysis of wholly self-referential systems would require an infinite amount of computational resources to predict outcomes. It's also a metaphysical assumption that needs exploring, but that's where this comes in. So this is really what defines determinism without predetermination. These are some technical terms for the experts of you who want to know about this. So why is this so important to say? Because it's always been said, well, deterministic theories, they operate on the basis of pre-existing measurement outcomes. And that would be totally incompatible with the predictions of orthodox quantum theory. But in emergent systems, quantum mechanics, and hidden variables theories, deterministic ones, they have these sensitive dependencies. The measurement outcomes are described by what we could say as emergent processes, and they describe the transition of indefinite ontic structures to definite ontic structures. So we have an ontological indefiniteness, and this is, for example, the quantum potential in Bohm's theory. So this was emergence, and now the remainder of the talk can look at non-locality, that big word. Is the universe local or non-local? And that is of course, this decisive and controversial issue, because de Broglie-Bohm theory is a non-local hidden variable theory, and it founds itself upon the idea that there exists a non-local ontology, not just a local ontology. And that is, of course, many people say that's just plain wrong. It can't work, right? It's in conflict with the special theory of relativity, and so on and so on and so on. But there is a solution, and it comes under the word action at a distance. Of course, it involves faster than light activity, or non-local causal influences. And I just will call that non-locality. What it entails is, though, a realism that is contextual and non-local at the same time. That needs to be developed. This would be the future theory in view of the non-local. And let's look at what action at a distance and non-locality means. And this is mostly for the non-experts here. Just to remind us, what are we talking about when we say non-locality in the laboratory? Because so far, we've only observed it in the laboratory, not in nature. Let's assume we have a lab on Earth, orbiting Earth, and a lab on the red planet, orbiting Mars. And this is a quantum entangled pair, of an EPR-type correlation experiment. And then I send one of these particles to the Earth-based lab, and the other of these particles to the Mars-based lab. And so we have a measurement on the blue planet and a measurement on the red planet. And then our experimenter Alice performs a measurement of a certain property, very simply put, on our particle X, which is entangled. And her measurement instantly fixes the measured value which that Bob will measure in his laboratory on Mars. And that's puzzling. And that's what we know as non-locality, that sort of observation. And a signal, though, if there would be a signaling going on that would be consistent with special relativity, that signal would take, on average, 14 minutes. This is the mean distance of Mars to Earth and how long light would take. And of course, that effect is happening instantly, beating the speed of light. And that's the big puzzle. And that's being confirmed in the laboratory many times now. And the way how to interpret this is, of course, where we have all the different quantum interpretations. And I'm going to talk about 4 of them specifically. And that's what in Bohmian theory would call a non-local influence or non-locality. It's bidirectional. It doesn't go from here to there. It's instant, so there is no traveling of signals, no propagation. And that's a strange kind of causality. Let me define what this means. So there's a non-local action between A and B that is instantaneous in a common rest frame. The non-local action extends without limit, and it does not decrease with any spatial difference between these locations. We could have these labs separated halfway across the universe. That's an assumption that is made. The non-local action is specific only to the individual members of this entangled pair. And finally, the non-local action cannot be used to transmit signals and for communicating any messages between A to B. So there is no Bell telephone. You can't use this to communicate, of course. That would be a violation of special relativity. Now, these are just 3 experiments you've all noted over the years. You know, this has the most recent one on testing this came out is by the Chinese satellite-based studies, which showed 1,200 kilometers. Now, this is the record right now for showing non-locality in these systems. But Nicolas Gézin already, who's going to speak tomorrow, showed 18 kilometers distance. It holds for that. And here in 2015, Hansen, with the Dutch group, showed this for electrons even, up to a distance of 1.3 kilometer, which was the most loophole-free test so far to prove non-locality in this case. But the key question is, of course, you're sitting here, people who are into Copenhagen, who are into operationalist quantum mechanics will say, but wait a minute, there are no non-local influences. You don't need them. So the key question is, are these non-local connections, what is sometimes called action distance, merely a mathematical construct, as in the orthodox view, like Copenhagen? Or are they non-local anti-causal elements in a radically new conception of reality, a form of quantum reality or quantum causality, which still needs to be defined and discovered? And that's the big battle that's going on, and that Bohm has always brought this out, and people have been discussing this now for decades. Why is this important? Because we're looking at 2 different interpretations of the universe. In the one, in a Bohmian universe, we're living in a non-local universe, which is fundamentally interconnected. In the other interpretation, in the more conventional ones, orthodox ones, the universe is entirely local. And the non-locality is really an operational illusion, which you can explain away, or which we can account for in different ways, without assuming the existence of non-local causes. So, for example, in the orthodox quantum mechanics, like Copenhagen, there are no non-local influences assumed. There is no reality behind all this. And there is no scientific explanation given for these correlations in any ontological causal terms. In realist anti-quantum mechanics, and I'm really drawing on a distinction that Howard Wiseman has made, and I learned from him, he's made the case of we should really be very clear about the operationalist approaches to quantum mechanics, and then when we discuss that against realist approaches to quantum mechanics. And of course, Bohmian approach is a realist approach to quantum mechanics. And of course, there we do assume the existence of some kind of ontology, an ontic influence of some sort, and which would then be explanatory in the old-fashioned sense of science, that an explanation requires an understanding of reality and not just of mathematics. And we're going to go into that a little bit more. So here, in ontological approaches, one talks about an ontic state lambda, and there's many different approaches how to work with this, and one would be a non-local ontic state, like in de Broglie-Bohm. But very recently, and I'm glad we have speakers on this topic at this conference, time-symmetric ontic states, analyzing. It's very well known that in quantum mechanics we have absolute time symmetry at the heart of it. But does that translate to the ontological level if it exists? And there's a big debate about that right now, and we're going to have speakers speaking to that. And that would be a local explanation, but a retrocausal one, where the actual effects are from the future to the present or past. And that's an alternative position to non-locality, where you deal with these strange properties of space. In the second case, you would explain these correlations by dealing with the strange properties of time. And both are equally valid right now, as far as we know. So the distinction I want to draw for all of you as we go through this meeting, to learn to understand the difference between operational epistemological approaches on the one hand, and this is called operational quantum mechanics here, and the realist approaches. Operational about what we can know about the world, epistemology. Ontology is about what is real in the world. And of course here, Einstein, Schrödinger, de Broglie with pilot wave theory in the beginning, that's why I've been in brackets. He later switched to the operationalist approach, but he was the inventor of the pilot wave idea. And Bohm and Bell, they are found on the realist side. They were really interested in what's the underlying reality here. And of course, the operationalist side, we have Bohr, Heisenberg, Pauli, Born, von Neumann, and many others. So this is the textbook view. This is the alternative view.